last year in pre-calculus, in our pre-calculus book, we talk about being continuous and not continuous and different types of continuity. Being continuous and knowing whether a function is continuous tells us a lot about things in calculus. And so we're going to talk about continuity quite often and how it relates to calculus. Today we're just pretty much talking about whether something's continuous and what type of discontinuity that it has. So I find it to be a very weird word. But so I printed this out for you, mostly because if you turn the page, there's a bunch of graphs on here, more than anything. But definitely feel free to add in your own stuff as you're going through here and stay focused here. We talked about this last year. A really easy way to think about a continuous function is if you could sketch it without ever lifting your pencil up, then that would be a continuous function. Like sine and cosine, those are continuous functions. Tangent, not continuous, because you have those asymptotes, which means you'd have to pick your pencil up in order to do that. Linear functions are continuous. Parabolas are continuous. So your book defines it like this. If a function is not continuous at a specific point C, we say that it is discontinuous. Here's an important thing to notice. C does not have to be in the domain of F to talk about whether it's continuous or not continuous there. We'll talk about this a little bit more when we get to another example. I feel like throwing in the whole is it in the domain or not makes things a little confusing, but that's just how we roll in calculus class. So like it might be in the domain, but it need not be in the domain. I don't know, because that doesn't sound cool enough. All right. I think we talked about these last year. Sometimes I get confused. But these are the types of discontinuities that we think of the most. A removable discontinuity is one that can be made continuous with only one point. And we'll look at an example of that in just a minute. But if there's just a hole in the graph, that means there's like one little bitty hole. If you put 1 point in that graph to fill that hole in, it would now be a continuous function. That's the idea of a removable discontinuity. I think it's discontinuity, but I continue to say discontinuity. What? I want to make sure I write these the way, oh yeah. Can be filled in with 1 point. So a good example of that is a hole in the graph, and we'll look at one of those in just a minute. A jump discontinuity is just exactly what it sounds like. It's like when your graph jumps from one thing to the other. So it is a break or gap in your graph. A good example of a jump discontinuity is a step function. At each step, that is a break or a gap, like it jumps up. You definitely would have to lift your pencil up. Tangent would not be a jump because tangent would be classified as an infinite discontinuity because it has that vertical asymptote that the graph doesn't just stop here and then jump to here. In a tangent one side keeps going up forever, and then it goes over to the other side. Does that make sense? And so if you have an asymptote, that is an infinite discontinuity. That's my definition. Infinite is an asymptote. Vertical, just vertical. Because when we're talking about discontinuity, we're talking about x values. We're talking about not being continuous on the whole domain. Does that make sense? So I'm normally talking about vertical asymptotes. I feel like if there's a horizontal asymptote, do we have any functions that have just a horizontal asymptote and not a vertical asymptote? I'm trying to think, because I feel like they go hand in hand. Like a rational function has both. I don't know. I might have to think about that one. I'm not really sure. I've never really thought about that before. when the answer that I can give you right now is when we're talking about being discontinuous, we're talking about the domain values, which are the x values, which means we're talking about vertical asymptotes. The last type is one that I think shows up very rarely, except for in that one section when they make you say which type is which, and that's called an oscillating function. And the definition of an oscillating function is it oscillates. You know what that word means? Oscillates. Oscillates? I don't even know how to spell that. It means it kind of just keeps going like up and down, up and down, up and down, up and down, and we'll look at an example of that in just a second in your book. It's not an asymptote, like it doesn't just keep going up and down forever, but it kind of goes like this. As you get closer and closer to a point, like this side goes up, and this side goes up, and it's just really weird. I don't know. It's weird. That's why I said I don't think it shows up very often, but... Here, look, we're going to write this. Has no limit at points of discontinuity. And the next page I have pictures for you, which is why I printed this out for you, and you'll see what oscillating means. And I took these from your book, and so it might not have copied super well. I know on mine I kind of drew my own points in here, so you might have to fill a little bit in here. But I'm just going to kind of give you an example of all these different types of functions. Guess which one's oscillating? So, we're just going to start up here. You might say A, B, and C look exactly the same, but they are a little bit different. A is just a nice little continuous function. So there's no breaks, there's no gaps, there's no holes. This is continuous. And we're assuming that it goes on forever and ever, but we can say it's continuous from negative infinity to infinity. B, I don't know if you can see this on your paper, but B looks just like A, except for right here at 1 on the Y, that's an open circle, so you might need to make that on your graph. So that's an open circle. Which means what type of discontinuity does graph B have? Removable. We're going to name it as our type. We're going to say this is a removable. And I always want to put an E on removable, but I don't think it's supposed to have one. It's removable because if we filled in that one hole, it would now be a continuous function. Part of your homework is going to ask you to say, and what we're going to do one of these in a minute, but it's going to say on what intervals is it continuous. For this one, we would say it's continuous from negative infinity to 0, because we're talking about the x values. We want to write that here. Continuous from negative infinity to 0, not including 0. And then it picks right back up, it's continuous again from 0 to infinity. And remember, if you're writing like two things, you can use a little intersection, or if you just wrote and, it's okay. Both. Like some would just have a graph, and some are just going to have equations. Part C, or letter C, this is a piecewise function. Difference between B and C, we still have an open circle here, but now we have a filled in circle up here, which means we could write that as a piecewise function. What type of discontinuity is letter C? It's definitely not continuous. Like, it's definitely not continuous. Like, we can't say it's continuous, even though there's a point up there. But, is it removable? Could we just fill it in? Could we make that a continuous function if we just fixed one point? Is that dot just one point that's our issue? I think it's still removable. That's why we're on this page. These are all called non-removable. part of your homework, they just say, is it removable or non-removable? Well, if it can't be fixed with just a point, it's called non-removable. I think C is removable, because if I had this, you're right, the difference is, on part B, I could just fill it in with my pencil. On part C, what if I just picked up that one point that's up here, and then stuck it right there? Is that still just fixing one point on the graph? Theoretically speaking, if I wanted to make it a continuous function, I could pick that dot up and I could move it down there. So let's see if it's letting me.
Oh my gosh.
I fixed it with 1 point. Yeah, this is like I can move any of this, like when I write. I just usually don't have a need to move it.
Alright, that's way too
So this is also a removable discontinuity. Removable and non-removable is going to become a big part of knowing whether a limit exists or not. So that's why that's kind of important. I think all the ones at the bottom are going to be non-removable. And let's just say which kind they are. Letter D, what kind of discontinuity? Yeah, it jumps. It goes and it stops at 0, and then it jumps up to 1. So this would be a jump. And I'm just going to say at the same time that's non-removable. And letter E, infinite, that's definitely an asymptote there. This side's going up, this side's going up, but they're never going to meet, they're never going to touch. So this would be infinite, also non-removable. And F, again, I feel like oscillating never shows up except for when they first tell you about what kind of discontinuities could exist. So I feel like this isn't a huge issue of knowing this, but it is an oscillating one, which would also be non-removable. What? Let's do an example. That's a great idea. So Sarah said, are they going to give you graphs or equations? Well, if they give you a graph, it should be pretty easy if they give you a graph, because it's nice because you can just look at it. The harder part's going to be if they give you an equation. And what I am going to suggest to you, the same thing with limits, is try to figure out what you can figure out without just graphing it first. And then if you want to graph it to check it, you can. But don't become so dependent on that graphing calculator, because you're not going to get to use that graphing calculator every time we have a quiz or a test. On half the AP test, you're not going to get to use it. So if we're looking for points of discontinuity, we're looking for breaks in the domain. We're looking for things that X can't be. So what could you tell me, just from looking at this equation, a problem that you know we're going to have in this graph, a point of discontinuity? Because if I plug 1 into this equation, do you agree I'm going to get 0 in my denominator? So I know without even making a graph that at x equals 1, I'm going to have a point of discontinuity. At x equals 1. Do you know what kind of discontinuity that's going to be without having to graph it? What did you say? I think it's going to be an asymptote. Do you agree with that? How do you find vertical asymptotes? In the denominator, right? You set the denominator equal to 0 and you solve it. That gives you your vertical asymptotes. If it's a hole in the graph, that means something in the top cancels with something in the bottom. If it's a jump, or even the one with the other kind of hole in the graph, that's going to be like a piecewise function or a step function. If you can't cancel anything out and it's in the denominator, that's going to be a vertical asymptote, which means I know this is an infinite discontinuity. And you could check by graphing it. And it definitely has an asymptote when you graph it. But I just want to again, push you in the direction of trying to do these without your calculator, because when we have a test, a lot of these are going to be without a calculator. Okay, so that's not so bad. So now let's see if I can make things more confusing. So we can talk about whether a function is continuous on an interval, whether it's a continuous function, whether it's continuous over its domain, and we can get really specific here. So this says a function is continuous on an interval if and only if it's continuous at every point in the interval. So a problem could say, is this function continuous between 0 and 7? And that means the only values you're looking at are between 0 and 7 and seeing what happens there. You don't care what happens outside the interval. A continuous function is a function that's continuous at every point of its domain. I find this to be very confusing because when you look at a graph, it looks like it's not continuous, but if you look at the domain of the function, then it can be continuous. And so let's look at this example, and I'll show you what I mean by this. So it says, is the function y equals 1 over x a continuous function? In the domain of that function. So let's think about for a minute, for example 2, if I have y equals 1 over x, what would you tell me the domain of 1 over x is? Is it all real numbers? Everything except 0. Do you agree with that? So I could say the domain, well, I'm going to write an interval notation. The domain would be negative infinity to 0, and then picking back up at 0 to infinity. Everything but 0, exactly what Morgan said. We should know what the graph of this looks like. If I pick like 1, I get 1, and 2, I get 1/2 and 1/3. If I pick fraction, it's going to go up, so it's going to kind of look like this. And I pick negative numbers, I'm going to get the same thing, but it looks like this. So the question is this a continuous function? And the definition of a continuous function is one that's continuous at every point of its domain. Does this function have a y value? Is it continuous at every point in its domain? Do you find how that's a little bit confusing? Because don't you want to say it's not continuous at 0? I want to say it's not continuous at 0. It doesn't go to 0. That's what the book's saying. An infinite discontinuity, right? That's what it seems like it has. And it's true. Like, we're going to write that down. We can say two things. We can say it's a continuous function because it meets every point of its domain. But we could also say that there's a point in discontinuity at 0, it just happens to not be in its domain, which I find to just be ridiculous. You're right, there is no break in the two lines, but if you go back to the definition of an infinite discontinuity is just when there's an asymptote, because you would have to pick your pencil up to graph this. Do you agree with that? Like, that's my issue with it, and maybe I make it more confusing than it has to be, but I kind of struggle with the two things. So here's what we can say. We can say, yes, it is a continuous function because it is continuous over the entire domain. Right, that would be the domain of this function. If this question asked you, are there any values of discontinuity on that graph, you could still say, yes, there is a point of discontinuity at x equals 0. And I'm just going to go ahead and add this in, but x equals 0 is not in its domain. So here's what I want to caution you about on this. Make sure you read the directions. If the directions say give all points of discontinuity, you're still going to give you would still give x equals 0 on this problem. But if it says, is it a continuous function, all you're looking for is it continuous over its domain. The good thing about AP questions is I feel like they always give you an interval. Like they say, is this function continuous from negative infinity to infinity? Or is it continuous from 7 to 10? They give you that interval to look at, so I feel like this doesn't come into play a lot, but it does come into play in this chapter, and so I wanted to make sure that I take some time to talk about this, because I know I kind of struggled with it for a minute. Okay, let's keep going. Piecewise functions, they're my favorite. Graph and find any points of discontinuity, label as removable or non-removable. So hopefully we're feeling pretty good about points of discontinuity. Piecewise functions, these are both linear graphs, so I feel like we could graph this pretty easily. 3 minus x, when x is less than 2, so here's going to be my kind of dividing point here. I'm going to have a y-intercept of 3, a slope of -1, and I'm going to stop at x equals 2, because I'm only going to put this piece of the graph when x is less than 2, and I think I would get something roughly like that. This is x over 2 plus 1. That's the same as saying like 1/2 x plus 1. This one's only when x is greater than 2, so you could start at 2, or you can kind of just visualize it. I usually just kind of visualize it here, so let's see if we can agree on this. I'd have a y-intercept of 1, but I'm not going to make a mark there. And I'm going to go up 1 over 2. I think I would have an open circle on that one too. Up 1 over 2, up 1 over 2. And it kind of roughly look like that. Yes.
So, like, obviously this is discontinuous, but if one of those,
Nothing. It is definitely discontinuous.
okay, but if one of those was a closed circle and not an open circle, it would be movable. Oh my gosh, I have no idea. I don't know this. Why is it hard to just move it down?
But do you see how there's a gap here? Like there's a jump between this piece of the graph and this piece of the graph? It's not just that one dot that was above there. The only time it's removable is if it's just one hole in the graph, or it's one hole in the graph with one dot right above it or right below it. That's the only time that it's going to be removable. This one is not removable because, you're right, even if one of them was filled in, it would not be removable because this piece is going good, it stops, and then it jumps up and keeps going. We couldn't fix it with just that one. Like if we filled in this one, or even if we fill in this one, we still have a problem. I'd have to fill in the dot and move that whole piece to make it match up. So I'm going to say, where's my point of discontinuity? At x equals 2. And this would definitely be non-removable. I think we could even say it's a jump discontinuity. Dang it, let's do that. I don't know what I did this time, kids. Okay. How about this, Sarah? What if, pretend this is a new graph down here. What if it went over like this? Oh yeah, and then, okay. What if it went like this with an open circle, and then the other one started right on top of it and then went like that? Would that be discontinuous? It's still an open circle. Would that be removable or non-removable? But could I fix it with one dot? You could fix it with one dot. Yes. Yes.
Yeah, 2 dots,
remove something. Like on this one, like let's just say this was filled in. We still couldn't fix that with just one dot because I would have to take this and move it down in addition to moving that one dot down. Like I'd have to do a lot to fix that. I could move the dot, but I'd also have to move that graph so that it matches up, so there wasn't a break, a jump, a gap is what I'm looking for there, not just one dot. All right, I really want to finish this one, and we'll stop at the intermediate value theorem. We've done this lots and lots of times before. It's just different directions, so I just wanted to show you this. It says, give a formula for the extended function that's continuous at the indicated point. That just means use some algebra to get to a way that it wouldn't be undefined at -3. So at this problem, do you agree that at -3, if I plug -3 in here right now, I'd have a problem? Because I'd get 0 in the denominator. Like I actually have an asymptote at -3. All they want you to do is make a new function. Basically find what it would be if you took the undefined part out. So I think I could just factor this, right? I could get x minus 3 times x plus 3 on the top. And then I could cancel that out. Find the extended function that's continuous at the indicated point. Well, the extended function would just be what's left over. It's just x minus 3. This is an example of a hole in your graph. Like if you had this function and you graphed it on your calculator, it's going to look just like a linear function, but at -3, there would be a hole in the graph. Like this would be an example of a removable discontinuity because we could fix it with just that one dot. Okay, so I just want to show you that directions. We'll start with the intermediate value theorem tomorrow. I don't think there's really any homework over intermediate value theorem.
Teachers, please excuse the interruption. I have one.
This is what's on your assignment sheet.
Drivers, we're going to be checking parking tags here in the near future, so